Today, we're going to dive into what I think is one of the greatest detective stories in all of science, the hunt for the atom. I mean, it's the basic building block of literally everything. But what it actually looks like, well, that's been a puzzle for centuries.
So let me ask you, when you close your eyes and picture an atom, what do you see?
If you're imagining a tiny little solar system, with little planets zipping around a sun, you're not wrong. That's a great starting point. But as we're about to find out, that popular image is just one chapter in a much more fascinating and, frankly, way weirder story.
So, let's get into it. That mental image most of us have, it turns out it's got some pretty serious flaws. And understanding why it's flawed is the key to understanding how our world actually works at the most fundamental level.
So check this out. This is our roadmap for today. In just over 100 years, our picture of the atom got a complete makeover 5 times. We're going to follow this timeline and see how each new discovery didn't just tweak the old idea, it completely shattered it and got us one step closer to the truth.
Our story kicks off way back in the early 1800s with 2 pretty simple but really powerful ideas that basically set the stage for everything that was to come.
First up, you've got John Dalton. He pictured atoms as these tiny, solid, indestructible billiard balls. Simple, right? The name itself even comes from the Greek atomos, which means uncuttable. For Dalton, this was the end of the line, the smallest thing possible. A really powerful and, elegant idea. But of course, this simple picture was about to get complicated. Just when science thought it had things locked down, a brand new clue emerged. In 1897, a physicist named J.J. Thomson discovered something that, according to Dalton, shouldn't even exist. A particle that was even smaller than the uncuttable atom, and we know it today as the electron. So this just created a huge problem for the old billiard ball model. Thomson had to get creative, so he cooked up this new idea, the Plum pudding model. Just imagine a ball of positively charged goo or pudding, with these tiny negative electrons just kind of scattered throughout it, like raisins. It was actually a pretty clever solution, because it incorporated the new electron and it explained why atoms are electrically neutral. And for a little while, plum pudding seemed to work out. But then one of Thomson's own students, a guy named Ernest Rutherford, set up an experiment that was about to blow the whole thing wide open. What he found was going to change physics forever. Okay, so here was the plan. Rutherford's team was going to fire these tiny, positively charged things called alpha particles at a sheet of gold foil that was so thin it was practically transparent. Now, what's really interesting here is what they thought was going to happen. Based on that plum pudding model, where the positive charge is just a soft, spread-out mist, those little alpha particles should have just punched right through it, maybe getting bumped off course just a tiny bit.
But that is not at all what happened, and I think it's best to let Rutherford describe the shock in his own words.
That quote? That was the sound of physics being completely rewritten. Because while most of those particles sailed straight through, that tiny, tiny fraction, just 1 in 8,000, bounced back. That tissue paper was firing back. The plum pudding model wasn't just wrong, it was dead. This wild result could only mean one thing. The atom had to be mostly empty space. Nearly all of its mass had to be crammed into an impossibly dense little center which Rutherford called the nucleus. Now, to really wrap your head around this, picture a huge sports stadium. That entire stadium represents one single atom. You know where the nucleus is? It would be a single marble, sitting all by itself on the 50-yard line. Everything else is just empty space. Wild. But of course, in science, when you solve one huge problem, you almost always create a brand new one. And this new nuclear model, it had a huge, catastrophic flaw. I mean, think about it. The nucleus is positive, the electrons are negative. Opposites attract, right? So according to all the laws of physics at the time, those electrons should have immediately spiraled into the nucleus and the entire atom would just collapse in an instant. But they don't. The world around us is stable. So what was going on? The next piece of this puzzle came from a physicist named Niels Bohr. He proposed this radical new rule. He said electrons can't just be anywhere they want. They're locked into specific energy levels, or shells, kind of like planets in fixed orbits. An electron could be on one level, or it could jump to another, but it could never, ever exist in the empty space in between. And Bohr's planetary model, it was a massive leap forward. It worked perfectly for simple atoms, like hydrogen. But the second physicist tried to apply it to anything more complex. The math just fell apart. The puzzle was a long way from finished.
And now we get to the final and definitely the weirdest piece of our puzzle.
In 1926, Erwin Schrödinger basically dragged physics into the bizarre world of quantum mechanics, and our nice, simple picture of the electron was about to get completely obliterated.
So Schrödinger's math showed that we have to just completely give up on the idea of an electron having a neat, predictable path. This is the key. We have to stop thinking about a fixed orbit, and we have to start thinking about a fuzzy orbital. It's a huge shift, from thinking of a planet on a track to thinking of a cloud of probability. From certainty to, well, uncertainty.
So what is an orbital then? It's just a 3D area where you're most likely to find an electron. Here's the best way to think about it. Imagine a mosquito is buzzing around inside a dark room. You know it's in there, you can hear it, but could you point to its exact location at any given second? No way. The entire room is the orbital. It's the zone of probability for that electron.
And these orbitals have all sorts of weird shapes. So you've got this tiny little nucleus, and it's surrounded by these fuzzy electron clouds. These are not flight paths, okay? They're more like three-dimensional maps showing where the electron is most likely to be found. The darker, denser parts of the cloud are the high probability zones, and the thinner, wispy parts are low probability.
And it's not a total free-for-all. The electrons follow this surprisingly orderly set of rules, kind of like finding a seat in a stadium. First, they always fill the best seats, the lowest energy levels. Second, only 2 electrons can fit in any single seat or orbital. And third, they'll always take an empty orbital in the same row before they're forced to pair up. This predictable pattern is the key to absolutely everything.
So why should you care about this weird cloud? Because its shape and its rules dictate everything. This electron arrangement is like the hidden engine that drives our entire world. It controls how atoms bond together to make molecules. It controls how chemical reactions happen. It even controls how electricity flows. The behavior of these quantum clouds is chemistry.
And this is the payoff. This is what those quantum rules actually build in the real world. Everything from life-saving medicines like penicillin to the very DNA that makes you who you are. It all starts with the strange, beautiful, and weirdly predictable rules of the electron cloud.
So think about this. Our picture of the atom changed 5 times in just a little over 100 years. Each model wasn't really wrong, it was just the best possible story based on the clues scientists had at the time. The quantum cloud is our best model right now, but you can bet this detective story is almost certainly not over. Which leaves us with one last thought. What new discovery is waiting just around the corner? And what will the next picture of the atom look like?